want to talk a little bit about what it means to take the span of a set of vectors. So the definition of the span of these k vectors here is the set of vectors in our vector space capital V that have the form a constant times v1 plus a constant times v2 plus a et cetera, plus a constant times vk. Really, what this is saying, I should also mention the constants are all in some set that I call F here. It could be the real numbers or the complex numbers. But what this is saying is that the span of these vectors is the set of all possible linear combinations of those vectors. That's what this set notation is really saying. Linear combinations of vectors means I do scalar times vector plus scalar times vector. And every single possible way that I could combine these vectors is what makes up the span of those vectors. So let's look at a quick example of the span of a set of vectors. Let's say I want to find the span of the vectors 1, 2, and 3, 1 in R2. The span of these vectors are all the linear combinations I can make with them. So this is going to be vectors in R2 such that those vectors look like C1 times the first vector 1, 2 plus C2, another constant, times the vector 3, 1, where C1 and C2 are real numbers. Another way to write this, if we went ahead and just combined this expression, we'd have all the vectors in R2 that have the form V equals C1 plus 3C2, that's the elements in the first component, plus 2C1 plus C2. C1 and C2 are real numbers. So any vector that has this form is in the span because it would be a linear combination of these two vectors. For example, if C1 were 1 and C2 were 1 as well, we could say that 1, 2 plus 3, 1, which gives us 4, 3, 4, 3, that is in the span of those two vectors because I can write it as a linear combination of them. Same thing if I had taken C to be 2 and C2 to be -5, I would get a vector by doing that linear combination, and that vector would also be in the span of those two vectors. I'm going to go ahead and delete this to give myself some more room. Okay. And I want to talk a little bit about some of the phrases you'll hear or read in the textbook and what those phrases mean. So the first phrase I want to talk about is when you hear that V, a vector, is in the span of a set of vectors. Vk. Okay. What does that mean? Well, that means, maybe I'll write this over here, that means that the vector V can be written as a linear combination of the vectors in that set, V1, V2, all the way to Vk. We just saw an example of that. I'll write it again. Maybe I'll write a different example. I can say that -4, -5 is in the span of 1, -1, and 2, 1. Why do I know that? because I can write -4, -5 as a linear combination, c1 times the first vector plus c2 times the second vector, for some scalars. In fact, I can tell you what those scalars are. So for some scalars in R. So in fact, let's write this down. I know that -4, -5 is actually equal to 2 times 1, -1 minus 3 times 2, 1. So I didn't show you how I know that. It's just, this is an example that I had prepared before, so I know it from that. But the point of this is that 2 and -3 are exactly scalars, those scalars c1 and c2. And this 2 times 1, -1 plus -3 times 2, 1 is a linear combination of those original vectors. So I know that because I can write -4, -5 as some combination of the two vectors, then this vector, -4, -5, is in the span of those two vectors because it is one of the possible linear combinations. Remember, the span contains all possible linear combinations. -4, -5 happens to be one of them, so it is in fact in the span. So that's what that phrase means. If you have a vector that's in the span of other vectors, then the vector that you have here can be written as a linear combination of those vectors in your set. Okay, the next phrase that I want to help us digest, so phrase number 2 here, is if you hear that a set of vectors v1 to vk spans some space. I'll call it V. The set spans V. What does that mean? That means that the entire vector space, capital V, can be generated or created or built, if you want to think of it that way, can be generated by taking linear combinations of those vectors of v1 through vk. The whole thing. Another way of saying this, I'll write this right below, this is the same as saying that the span of those vectors, v1 to vk, is equal to v. If I take all the linear combinations of those vectors, I can create v. So let's look at an example. I can say that the vectors 1, -1, 0, 1, those two vectors, this set of those two vectors spans R2. Okay, so if I try to write out what that means, it means I can create any vector in R2, any vector x, y in R2 by taking linear combinations of those vectors. So using a linear combination, x, y equals some constant times the first vector, 1, -1, plus some other constant times the second vector, 0, 1. You can actually figure out what these constants should be. They'll depend on x and y here. That can sometimes be a little confusing because you were used to thinking of x and y as unknowns. In this case, x and y are playing the role of general elements or general components of vectors in R2. And C1 and C2 are the unknowns in this case. These are the scalars we want to find that will just depend on x and y. So let me do an example to give you a better sense of this. I've already figured this out on my own time, that C1 and C2 are going to be, this relationship is going to be that xy, any vector in R2, can be built by multiplying x times 1 comma negative 1 plus x plus y times 0, 1. So in this case, x is our constant C1, and x plus y is playing the role of our constant C2 for this particular set of vectors. So for example, if I had the point negative 3, 5, well, if I wanted to create that make that a linear combination of 1, negative 1, and 0, 1, I'm going to put the first component here, that's my x, times 1, negative 1, plus x plus y in this spot, well, that's 5 minus 3, that's 2, times 0, 1. So again, this 2 here is playing the role of C2, this negative 3 is playing the role of C1. And maybe to make this even more explicit, this was x comma y. Our negative 3 was C1. 1, negative 1 is our first vector, V1. The 2 was C2. And 0, 1 was our second vector, V2. Let me give myself a little bit more room here. Okay. So if a set spans a vector space, that means if I take the span of that set, I can generate the entire vector space V. That means I can create V just using linear combinations of the vectors. That set of vectors spans V. All right, the last phrase I want to discuss is if you kind of hear this phrase that the set of vectors V1 through Vk, oh, let me move that really quick, is a spanning set, is a spanning set for some vector space. The set of just the vectors by themselves being a spanning set means that the set spans V. Okay? So again, it's kind of saying the same thing. It's saying that the span of V1 to Vk, sorry, not V2, Vk, gives you the vector space. So using our previous example, and I'll kind of rework it here, we saw that this set, 1, negative 1, and 0, 1, spans R2. That's like the verb, that's what it's doing. The description of the set is that it is a spanning set of R2. So we can say 1, negative 1, comma, 0, 1 is a spanning set. Spanning set for R2. Okay. So these are 3 different ways of using the word span. If we have a vector that's in the span of a set of vectors, then that vector can be written as a linear combination. If a set of vectors spans a space, that's like the verb, it spans it. That means if I took the span, I would generate that vector space. If a set of vectors is a spanning set, that's very much related to the second phrase up here. The set of vectors is a spanning set, that's kind of the adjective, the description about it. Then the verb, it spans that set. I can generate the entire set, V, using just linear combinations of those vectors.